Okay, thank you. I guess there are many vision conferences all over the world all the time now, and many people have been asked to contribute problems all over the show. And I have put some effort in making some problems to add to the Y2K problem, which is what I think what we are doing. This is all part of this big problem. And in some place I put down 10 or 11 problems which I thought about quite carefully but described them very briefly. So I thought I would take 4 such problems here and discuss them in some detail, putting them in context, which I think then naturally leads obviously to speculations. They are all unsolved problems. After the Dead Sea, I don't know what a good problem is anymore. If it's natural, it's bad. If it's false, it's probably good. So I will give my own adjectives later as to it's unnatural. I would have said these are natural. Some of them are very standard, but I just want to put a certain angle on it so that one understands the usefulness of these problems. They all have to do with L functions, the ones I choose here. The title of the talk had problems in analysis. I'll just introduce one there, which will naturally be, turns out, remarkably intimately connected to L functions. My lecture naturally follows that of Ivanich, so in a way, what he said, I think, is, or at least I can follow up on it in some forms. Now, as I said, what I want to say is about L functions. So you might ask, why L functions? What is an L function good for? It's a bit religious. I'll tell you a story a bit later about the religious, if I remember, and L functions. But in order to perhaps discuss that, I first have to define an L function, and then try explain a little bit why they might be important and why they are at the center of a certain kind of number theory today. So when I take this definition, an L function must be, of course, a series of the form an over n to the s, converging in the real part of s large. The an's needn't be integers, but the n's are integers. That sum is n, 1, 2, 3, and so on. So any series that somebody calls a zeta function, which is the zeta function of the Mindesakaram-Pleyel zeta function of a manifold, summation lambda j to the minus s, that doesn't deserve the name zeta function or L function. I'm going to put down what are the conditions before something, in my opinion, should be called an L function. So one is that it has a series representation, and as Henrik already pointed out, the second thing it needs is it has an Euler product. That is, that series should factor in the region where it converges into a product over primes of local L functions, and they should not be completely random themselves. They should take the form. So here m will be the degree of this L function. M is a fixed integer, and they should be rational functions of that type in p to the minus s for some coefficients, as stated here. Some of the alphas may be 0. These things may degenerate. Okay, so that's the definition of an L function, and of course, if that was the only part in the definition, this wouldn't be very interesting, because you put any alphas there, which are small, this converges, that's of no interest. The big thing that we seek, the religious thing we seek, is that this function have an analytic continuation and functional equation. Of course, I'll give the examples in a second of all the ones we know. But of course, it does start with Riemann, as you know. And that is that if we append to this Archimedean factor, as it is now called, which has the same structure as the factors for the primes, except that the gamma function replaces this function of 1 minus alpha p to the minus s, it too must be a product with m factors, m gamma factors, of the form gamma s over 2 with possible shifts. So notice the local factors have this data alpha 1 up to alpha m, and the Archimedean factor has data beta 1 up to beta m. These are numbers that go with the definition. And the thing we require is that the overall product, so I'll call it Xi following Riemann perhaps, that this product be an entire function. In the case of the Riemann zeta function, and it's the only case where there's a pole. In all other cases, my functions are supposed to be primitive or coming from cusp forms in a minute. And the only guy which has a pole in the world is this unique guy, the Riemann zeta function. All the others don't. So this should be entire and have a functional equation s into 1 minus s. It's not necessary to demand that it be back into itself. There's a dual L function which goes with it, and if I go s into 1 minus s and again s into 1 minus s, I will come back to the original function. But you can pretend that we only stick to ones which are self-dual. And of course, we have examples, as I said, the Riemann zeta function that you all recognize. And Henrik was talking about, can you see this at the bottom? It's very hard to push this. I suppose I can do that. The Dirichlet functions he was talking about, these are functions which are very similar to the Riemann zeta function. So the first 15 minutes, I'm assuming that the audience is general, and then slowly nod as I try to get somewhere. So hopefully this is still general enough. Zeta summation n to minus s, product of a p of 1 minus p to minus s to minus 1. That's just an identity reflecting unique factorization. The same with Dirichlet functions, introduced for the reason that Henrik mentioned, to prove there are infinitely many primes in a progression, but introduced by Dirichlet. The key thing about these characters chi is that they're multiplicative and periodic. So chi of mn is chi of m times chi of n, and chi is periodic of some period which is called always q. There are more general L functions. I'm giving you all the examples we know. So one of the favorite examples is one of the following modular forms. So let's let ls delta be the following series. Summation tau of n. This normalization divided by n to the 11 over 2 is just normalization to make every L function that I ever discuss have the functional equation s into 1 minus s. These tau of n's are given implicitly by the following formula. You take the discriminant delta of q, which is this infinite product for mod q less than 1, and you expand that in a series which defines these coefficients tau of n, which are usually named after Ramanujan, who first observed that tau of mn is tau of m times tau of n if m and n are relatively prime, and various other relations. Most importantly here is if you put q equal to e to the 2 pi I z, where z is now in the upper half plane, then this function delta of z, which has of course been known for many, over 100 years, goes back to elliptic function theory, delta of z is a modular form of weight 12 for the full modular group. What does this mean? It means that delta is an analytic function. It's given by the series. It's a convergent series in the upper half plane. And the modularity condition is that if I apply delta, so this is some discrete symmetry, which is the underlying feature of a modular form, delta of az plus b over cz plus d is cz plus d to the 12 times delta of z. This is true for every point in the upper half plane. And where abcd is in gamma, where gamma is a full modular group. Now, just as Henrik needed, the theory would not be that interesting if we just had SL2Z. One, of course, allows more than just this, but this will be enough for the illustrative purpose here. We will also look at subgroups A, where the bottom left corner is divisible by n. So n is a separate integer here in the definition of gamma naught n. So if you form this L function, it actually goes back to Mordell, that this L function is, or Mordell and then Hecker, that this L function is an L function in the sense that it has a functional equation and an Euler product. So this is quite different to the first example. The first examples were products where m equals 1. I didn't say so, but these are Euler products of degree 1. These are rational functions of degree 1. In P, 1 over, okay, the m is 1. And here m is 2. A very important example in modern number theory is the case of an elliptic curve. You start off with an elliptic curve over the rational numbers, defined over the rational numbers, and you form an L function. So this is a completely different description. This here, you start off with a geometric object, and you form an L function. This is where religion enters, and you hope this L function is good. So I'm not going to give the definition. You can find this in any book. Just let me say that the way the local factors, these are degree 2. This is a quadratic expression in p to the minus s, and I'm ignoring the primes dividing the conductor, so I'm of course being quite loose. You hopefully will allow me to do so. Let me just say the word. The key thing is that these APs here are given explicitly in terms of the analysis, local analysis of the elliptic curve over the field with p elements in the, when I keep away from the bad primes. So these are given by local data, and then the statement that that L function, that is an L function, meaning it satisfies something as remarkable as that, which is a very global statement. So the L function was, of course, originally introduced as a generating function. It's like magic. You introduce this function, then the analytic properties of this function start to tell you something incredible about the coefficients AP. I'm beginning to try to answer the question, why L functions? So this is an example which, as far as I understand from the newspapers and my colleagues, is now actually actually a theorem without any semi-simple assumption. Every elliptic curve gives a modular form, comes from modular form, and this L function is kosher, which is well understood in this country. Okay. We don't stop there. I'm listing all the L functions I know. And this is the way the subject has evolved for good reason. So here already the definition, I just have to say the words, but it's a generalization of the upper half plane. Instead, as Henrik wrote, the upper half plane is SL2R over over its maximal compact, which is rotation group. So in general, one allows GLM, and one doesn't. Once you go to the general case and to a number field or something, it's best to work representation theoretically, at least in formulating what a modular form is. And probably in the end you have to, when you go to these higher dimensional things, work in this way. But in any event, there is the generalization there of a modular form. I'll call it a modular form or an irreducible representation of GLMA, which appears in this. And there's something about how it behaves under the center. These are technical issues. The important issue is a modular form gives me locally a representation of GLMR, the Archimedean place, and for every prime P, an irreducible unitary representation of GLNQP. So already the theory of the representation theory, the unitary dual of such groups as GLN, SLNR, SLNQP, is a sort of a prerequisite to understand what the beasts are in the subject. But that subject is now, of course, under control. And of course, people could go ahead here even before that was under control. And it turns out, through the Heck operator theory or the spherical function theory, primarily Satake in these unramified cases, there's a way of associating for each Fp and F infinity numbers, which are the numbers that go into the definition of the L function that I had on slide 1. So one knows how to start off with a modular form and create these Archimedean numbers and the numbers for the finite P, such that the L function, which I will now, remember the L function has the product of the P's of LS Fp defined in that way, LS L infinity S F, and I will for later notation write LSF as a summation lambda. If I expand it in a series with some strange coefficients, I will call those coefficients lambda Fn. And for the reasons that I normalize the functional equation to be S into 1 minus S in everything that I ever write down, basically you should think of the lambda Fn's. Henrik was pointing out they sort of like characters, harmonics. In any event, you should think of them, they've been normalized to be size 1 on average. So lambda Fn are not plus or minus 1, but their modulus is roughly 1. So if I ever write down something that I want to estimate, that's the reason we normalize this way. By the way, all the people who work in the algebraic side of the subject will never normalize it this way. So there's already a easy confusion going on here. All right, so that's what the L functions are. Now, there's a belief. Now, this is really an amazing belief because it's a bit unreasonable to expect that every L function in the world is one of this type, but that is the way we understand it today. Even in the case for elliptic curves, that every elliptic curve, its L function should be modular, was something that I think Andre Weil, for example, in the early 60s was openly saying is a completely ridiculous, wishful thinking conjecture. But he changed his mind very rapidly. This is why I say religion. So that was a question of whether every elliptic curve is modular. But then in 1968, he wrote an important paper where he showed that if the L function of an elliptic curve is good in the sense that I wrote down, some more conditions about twisting, but allow me some freedom, yeah, then it's equivalent to being modular. And then he quickly changed his mind because when it comes to L functions, he just believes. No real, it's purely psychological. I mean, the belief that if you form the right L function, it's good, is just a belief which we have for any variety. Whether such things are true, of course, well, in general, is the problem. So that's certainly one direction the subject is taking. And constructions of modular forms in this way is a very major endeavor in the subject, and one which no doubt will be, if we're talking about next century, this no doubt will be around for the next 20 years because that's where the biggest breakthroughs have been made. But I want to really turn a little ahead of that, or some of you might think a little behind. But suppose I have a modular form. So those are the L functions, and the common belief for those are all of them. By the way, GLN is the only group. You might form on other groups, but then there's certain conjectures about functoriality. So there's only Euler products of degree n and only over Q. So this is supposed to capture the whole picture for primitive objects. Now, why is this so useful? GLM was just the matrix, the automorphic forms on the matrix, the size of the matrix group and the size of the Euler product. Okay. Now, why is this so powerful? Well, Henrik was already using a lot of this in various structures. The functional equation is a powerful thing. Riemann used it to outline, if you knew a little bit about the zeros, a proof of a prime number theorem. Riemann already understood why this is powerful. And he already understood that if you had a certain conjecture, which has been mentioned a number of times here, but I want to state it that it's its general form here. Just a conference like this should put out the big conjectures. This is Riemann's conjecture. Certainly, he only conjectured it for the Riemann zeta function. But let's call it the grand Riemann hypothesis. So there's something called GRH, which usually refers to the general Riemann hypothesis for Dirichlet L function. Now let's just say that all these L functions, this is a conjecture which by Gromov's definition, I'm not making this conjecture. This is an obvious conjecture once you've seen the others, unless somebody numerically shows you it's false. So this, right, this is obvious that this should be there. It's not stated because people don't think this grandly, but is it natural?
What is exactly the class that you consider?
Every automorphic cusp form on GLM, which is the only way, those are all the L functions that we know.
But not the ones you were listing at the beginning, not the problem itself.
No, those were special cases.
No, but I mean at the beginning you had written the functional equations.
I said, suppose you have a thing with an analytic continuation functional equation. It is all our belief that the only way you can form this is out of the L function of a modular form, cusp form on GLM. GLM is everything.
But that's two separate statements.
Yeah, one is a belief there, which is not so important because I don't think it's such a fundamental problem to try to prove everything comes this way because...
When you take the analog for function fields, it's false.
The word all.
Okay, can I continue? We're going to have a discussion, and if we're going to argue about that, then that's fine. Only with pleasure. Okay, so as I said, Riemann already understood the relevance of this to, for example, prove the prime number theorem. That's reasons why we want this kind of conjecture. Of course, probably everybody has heard that it's very useful, and I can just continue to say that. I'm going to give you only one example of an application outside of number theory of it later. I should say that Riemann, great conjectures must be A, falsifiable. Shouldn't be equivalence of categories of things that cannot be defined. Okay, they must be falsifiable. Riemann checked the first 10 zeros, and they were on the line. So he wasn't talking entirely. He suffered blood, like you wanted anybody before they make a conjecture. He checked the first 10 zeros. People have checked many more. You're not going to find one off, probably, because it's true. In any event, it has the characteristics of a great conjecture. Simple, powerful, and central to the subject. And however, that doesn't mean the subject hasn't developed. I'll get back to that. I should say it's the boring conjecture. If it were false, there was zero off the line. That would mean there's some great structure we haven't seen yet. And it would be much more interesting. If there's a zero off the line, it's because the primes and the say just for the Dirichlet L functions means there's some bias for primes to live in one progression rather than in another. That's got to be interesting. There's got to be a cause of that. So it's the boring conjecture. So sometimes the boring conjecture, this is, but if it weren't true, we'd be in trouble. I think it would be sad. I also want to emphasize that the usefulness, so I want to make some comments about this well-known conjecture. The usefulness of this conjecture lies in its knowledge for all, or at least many, large families. In the sense that if you told me that somebody proved the Riemann hypothesis for the Riemann zeta function, and that particular proof worked only for the Riemann zeta function, it's impossible, but suppose, of course, I'd want to see the proof, because clearly it would have to work in general. But suppose there was something, some trick somebody found. It's only true for the zeta function. There is no theorem that any of us could impress you with by just knowing the proof, the knowledge of the Riemann zeta function, of the Riemann hypothesis for the Riemann zeta function itself. If you knew it for all the Dirichlet L functions, we can write books. But if you just knew it for the Riemann zeta function, zero interesting applications. Except what? No, right, so I say pi of x as a remainder term, big O's, x to the half, log x, and you say, so what? I mean, no, I'm talking about applications, so, okay. Do you think that's good enough? Fine, but most people would say, all right, that's the remainder term. I should say that, as he just remarked, it's the natural conjecture in the sense that when you are trying to prove something and you're wondering what's true, you put in the square root cancellation. So if you have summation Mobius against any of these guys, any of these coefficients, the fact that that'll cancel like random numbers to square root and no beyond, and not beyond, as Henrik pointed out, is equivalent to the Riemann hypothesis. This is not a way necessarily of attacking it. It's just that's one of its uses. That's typically, if you want to use the Riemann hypothesis, how you might use it. And then finally, one of the reasons that we all believe it and that it's got a certain amount of sex appeal is that something along these lines was proved in the last 100 years. The analogs to which I'll return over a finite field are known. First, Weil proved the case of a curve over a finite field. I'll give an example later. But Deligne did the general case of varieties over finite fields, smooth projective varieties. Now, I should say Deligne's proof, this is very important for this talk, is very different to Weil's proof. In a way, Weil may have been lucky. He worked with one curve and proved one L function and proved it for that one L function. Deligne does not work with one zeta function of a variety. He puts it in a family, and then he uses a certain technique of families, which is the theme of this talk, and symmetry of the family, something called the monodromy group of the family. So his proof, even in the case of curves, is very, very different. He doesn't put the zeros on the line in just one step. He needs higher and higher representations of this monodromy group. These give you the zeros closer and closer to line and a half. It's an infinite process. And I think it's probably, and you'll see there are analogs, it's probably more likely that that kind of direction will yield, that kind of direction yields results. Whether it'll yield the proof of the Riemann hypothesis is another issue. Okay. So, all right, now, as Henrik said, he gave you some zero-free region, and it's fair to say that the subject, in some sense, of analytic number theory, just take for Dirichlet L function, at some level has failed miserably, because theorems towards a Riemann hypothesis, which say maybe there's a zero-free strip, just don't exist. There are no published ideas, let's say, towards a Riemann hypothesis. There are approaches this, but things which, are about to work, that doesn't exist yet. There are other things which I'll discuss in a minute. Now, the subject, however, exists. It's been a flourishing subject, and I want to just say a few words about it. The reason it flourishes is because there are many problems which a Riemann hypothesis would imply, and not just for the zeta function, as I said, and so you will have an unconditional theorem. You have a conditional theorem assuming the Riemann hypothesis, which eventually these techniques, like Henrik was mentioning, allow you to remove entirely so that the goal you are after is anyway resolved. So that's why the subject is really moved, is because it has resolved many problems that it set out to solve, but by sidestepping the Riemann hypothesis or by proving substitutes on average, one of which he put down. And in the case of Euler products of degree 1, this really starts with Linux, and then there's many names, including the names he mentioned, Bombieri, Vinogradov. In the case of GL2, that was the 50s, 60s, and 70s. In the case of GL2, this has been a development in the 80s and 90s, and I think Henrik is the name to mention if you want to mention just one. There are many contributors, but he certainly led the way. Okay, so much for that problem for the time being. I'm on page 6, okay. That's problem 1. It's a problem for the future. I want to describe what is apparently a simpler problem, but it's in the same subject, it's very closely related. It's a local problem. It's a spectral problem already. We'll discuss a bit later whether the Riemann hypothesis is a spectral problem, but this is already a spectral problem. And that's the following local problem. You take one of these global L functions, so you have this representation of GLMA of a GLMQ with something on the center and cuspidal. The word cusp form is important even though I don't define it. And then the local problem, which is due to Ramanujan, in this general form due to Satake, is the statement that those alphas that you saw in the definition should have certain bounds. This is probably not the right way to think about it, but it's the easiest way to describe it, that if FP is an unramified representation of GLM-QP or F infinity of GLM-R, then those alphas that you saw there, which you can check for Dirichlet L functions, this is true, for example, the modulus of those numbers is 1. That's just a statement that a character is modulus 1 in the case of one dimension. And the real part of the beta should be 0. So this is a far-reaching, very important conjecture, which goes by the name of the generalized Ramanujan conjecture. It has the feature that some special cases are known. It also has a very nice description of saying that the local representations you pick up here must be tempered. So there's a very beautiful group representation interpretation of what the Ramanujan conjecture says, but only for GLM. If you take other semi-simple groups, it's incredibly complicated. Nobody knows how to formulate it properly. And of course, I must add here that this Ramanujan conjecture itself was about that delta that I wrote down at the beginning, and that was solved by Deligne in his proof, using his proof of the Riemann hypothesis for varieties, and so he proved what Ramanujan posed. So you have all this fancy stuff, but Ramanujan, that's what he asked. Is tau of p, as defined earlier, less than 2p to the 11 over 2? And that was proved by Deligne, and of course is a fantastic result. Okay, I should say that in general this is far from solved, but as Henrik was saying, in many cases, and I like to call these problems pregnant. So he was mentioning this, and let me just say this again. Some people who look at the old-fashioned analytic number theory, they see a guy working there to improve by a bound by 1 over 137. And you say, what is he doing? You know, he's working, and there's like 200 pages, and the last world record was this, and it looks like gymnastics. And some of it is gymnastics and not interesting. But by and large, if somebody makes such an improvement, it's more likely that the person made a fundamental technological or new idea there, hopefully. That's one good reason to do such things. And the great reason to do such things there are many problems, and the set of such problems I'm going to show you one is growing all the time. Henrik pointed out two, where you know a bound, it may be the convexity bound, whatever he was talking about, where any improvement of the exponent doesn't just improve the exponent, but it completely resolves the problem you're after. Those are, of course, the Pearl problems. And there are enough of those, and those are the ones that I think are the most attractive. So, where was I? So here there's a natural bound that comes from local harmonic analysis on towards this conjecture here. Those are purely local. And recently, in this paper mentioned there, Lua, Rudnick, and myself were able to give the first global bounds in general. And they are quite sharp, in some cases even useful enough for what you're after. And I should say again, the method uses families, as Henrik was mentioning, whatever these families methods are. They also use Rankin-Selberg theory, which is what Deligne, what I think, according to him anyway, or according to Katz, when he asked Deligne, what is it that you knew that Grothendieck didn't know? His response was Rankin-Selberg L functions. That was the beginning of this family's argument. In that set of people, in that community, in analytic number theory, this existed, of course, earlier. So this Rankin-Selberg L function theory is used by us, and it's crucial. It was developed in general by Piasecki-Shapiro in his school, and Jacquet and Shalaika. It's an important part of the subject, and it actually shows concrete results of this type when used in certain ways. Okay, I understand recently that the brother of the guy you mentioned, so Lafourgue, his brother has recently announced a proof of the function field case of the Ramanujan conjecture. So that's where you take GLN of a function field. And he claims to have proved the Langlands conjectures, and in particular the Ramanujan conjectures. So since that's a very recent development, I must mention it. Okay, so where am I? All right, now, before I carry on these families, which is how I will end, I think it's crucial that I give an application. Now, Henrik gave a number of applications which were to classical number theory based heavily on the fact that in GL2, the defining equation of a 2 by 2 integer matrix is AD minus BC equals 1. And that's really why, that's what he was explaining, that's really why GL2 enters into certain things. What he was saying later was that if you take other symmetric spaces, or varieties realized concretely, Gromov says, give me a variety. Nobody gives a variety with equations, that's the trouble. That's the nice thing about SL2, it's AD minus BC equals 1. He's using the explicit form. If I give you G mod H in general, some symmetric space, and then you realize it through some projective embeddings and so on, you don't get equations. And unfortunately, the equations that we need to use to make progress, which are like AD minus BC equals 1, we'd like ABC minus DEF equals 1. That's no longer a homogeneous variety. That's where we fall dead. So the direction in GLM doesn't take you to homogeneous varieties. It takes you into some other information. And apparently its most powerful use thus far has been to understand GL2 better. Of course, they're going to people argue that. But even in the proof of Fermat's last theorem, in Langland's tunnels theorem, I mean, Fermat's last theorem about elliptic curve and GL2, but at some crucial moment, the symmetric square L function enters, and GL3 enters in a heavy, important way. So I think Langland's understood the boundaries of the subject. It hasn't shown its head here, but it does show its head indirectly by giving us new information in the upper half plane, the good old-fashioned upper half plane, to which I return now. So Sinai said something, and I want to explain one problem in quantum chaos, to which L functions are just made, for which L functions are apparently made, in some special case. Let me briefly tell you what this problem in quantum chaos is. Koifman amazingly described it this morning. I don't know why or how, but when I spoke to him, it was clear we were talking about completely different things. The words were the same. Amazing. So let's go back to the upper half plane divided by gamma naught n. This is a Riemann surface, or a hyperbolic manifold. I'd prefer to think of it that way here. Constant curvature minus 1 surface, a finite volume. Ignore the fact that it's not compact. All right, that is a special case of the following situation. In quantization theory, going back to the beginnings, you start off with a Hamiltonian, you quantize. If the Hamiltonian is completely integrable, which is the case Bohr studied, for example, one can understand after quantization, so I'm going to go to a specific example now, just let me say the words. You quantize this, introduces a self-adjoint operator on a Hilbert space with eigenstates, and there's this H bar, which Froelich said should never be going to 0, but God, I've got to make it go to 0, because otherwise I don't know what I'm talking about. So we let the semi-classical limit H bar go to 0. You have these eigenstates, and in the case that the classical mechanics is completely integrable, then it's well understood at various levels that the eigenstates start to concentrate on invariant tori, the invariant tori corresponding to the complete integrability. And this is why Bohr was successful in quantization without even having the Schrödinger equation. But if you start off with something which is classically chaotic, by which we might mean ergodic, with positive entropy, classical Hamiltonian, and you quantize, and then ask about the nature of the eigenstates, it is quite mysterious. And in fact, it was hopeless to say anything about such a thing, and that was never studied until 20 years ago when computers became powerful enough for physicists to start writing down thousands and thousands of eigenvalues and eigenvectors and trying to see in these chaotic cases what the eigenvectors look like. And they have good reason to ask this question. It's somewhat philosophical, how they behave in this chaotic case. And there are a lot of debates as to what should happen there. Rudnick and I worked on this for a while. And we finally decided that what they were saying couldn't be correct. It was based, Schnirelmann had a very major breakthrough about what happens to the average, or almost all eigenfunctions. But the question of what happens to every single one of them is very much up in the air. There's numerics suggesting one thing or another. We came to the conclusion, which seems to be now accepted. I don't know why exactly, but perhaps it's true. In this case, you'll see it's definitely true, is that these eigenfunctions, in the chaotic case, the following quantity should become equidistributed. So remember that if you're in quantum mechanics and you have an eigenstate, the thing that you naturally associated with it is phi squared, the volume, the Liouville measure. That's a probability distribution in the configuration space as to how this eigenfunction is. If you're a little more fancy, you introduce a function which lives in phase space. I'll ignore that. And you are asking when in the semi-classical limit how these behave. So in our case, if I take x to be the hyperbolic plane divided by gamma naught n, and the Hamiltonian flow is just the geodesic flow on the surface which is chaotic. I think Hop first proved it's ergodic and so on. And this is a no-soft flow. It's got all the properties of a chaotic flow. Then we are asking about the eigenfunctions here. An eigenfunction of a Laplacian, in this case, as Ivanish pointed out, is an automorphic form. It's what's called a mass form. So we could ask in this very special case, what's happening to the eigenfunctions? In particular, the probability measure we associate. So let F be a holomorphic form of weight K, like that delta for SL2Z, or a fixed subgroup of SL2Z. Let's form the following density. If it's holomorphic, we'll make y to the k f of z squared times dv of z. And if it's not holomorphic, it's just an eigenfunction, then k is 0 and ignore it. So to each eigenstate, there's this probability distribution of how it's sitting on the manifold. I ignore the phase space for simplicity. And the specialization of what we believe is going on there, that's Rudnick and myself, is that these things become equidistributed as the energy goes to infinity. Now, you might say this is the natural, obvious conjecture. It is, but it was not natural and obvious for us because everybody else from their numerics was saying other things. The numerics indicated scars and concentration on unstable periodic orbits. In fact, that's what attracted me to it anyway. Okay, we conjecture the opposite, and the reason we make such conjectures is because we can almost prove the opposite. So here's my next. So that's conjecture 3. It's not solved.
You make that in this arithmetic case?
Excellent question. I make it in the arithmetic case, and I'm ready to have my head cut off because it's naive in general. I'm going to make it in general, but that's brave, that's bold, and it's based only on the arithmetic case. And it's based only on the arithmetic case and what I'm about to show you. It may be completely wrong. It's like generalizing a phenomenon from the rationals to the reals, so to speak. You can go wrong very easily, and I've seen a lot of heads, but you know, you put your neck out after thinking about something for a while. Anyway, let's talk about the equidistribution conjecture. That will mean this case only. Take any holomorphic modular form of large weight, Hecker eigenform, everything's a Hecker eigenform, or eigenfunction of large eigenvalue, it should become equidistributed. Okay, now the remarkable thing, I put in inverted commas because the theory that's needed here, which is at the sort of the most sophisticated level of modern modular forms with certain dual pairs and seesaw dualities, and it's at present being worked out by a student of mine, Watson, the key breakthrough being due to Kudla and Harris, allows you to express, suppose I want to show that this measure is equidistributed. I take the inner product of this, I take this measure acting on some third eigenfunction, and there's actually an expression in this case that everything is Hecker eigenform, so it's highly nonlinear, of that expression in terms of L functions of automorphic forms or of Euler products of degree 3, 4, and 6. So you are, in trying to understand this problem, at least through L functions, you want to understand something in the half plane, but you immediately find yourself looking at much more complex objects. And that's kind of typical for these equidistribution kind of questions. And it's not only that you need the reformulation in this terms is that you need a subconvexity estimate. So Henrik explained that if you have an L function, there's this 3-line theorem. It's called Fragment-Lindelof in our world. It's 3-line theorem. You have a bound on the real part of S equals 1. You have a bound on the real part of S equal to 0. Those real part of S equals 1 is an easy bound, which you know. Real part of S equal to 0 follows from the functional equation. And then you have a 3-line theorem, which gives you a bound, purely interpolation bound in between. And as he said, nothing's free. Interpolation bounds will never give you the beef. So all you need in this kind of problem, and the problem he described, is a bound which is sharper than interpolation. So that's what you need in this kind of problem, but for Euler products of degree 3, 4, and 6. And I pointed out that we understand when I said that GL1 is understood and GL2 is understood, it means Euler products of degree 1 and 2 are understood enough so that subconvexity is in the pocket. But when we get to GL3, GL4, and GL6, we don't have the machinery to do it. However, luckily, we do have something which I was able to recently do. So I'll just say it in words because I'm running out of time. There's an Euler product of degree 4 that enters into this problem. The degree 3 I don't know how to do, but this looks harder, but for some reason this I can deal with. And you have an L function which, if you have two different modular forms in upper half plane, you form this series. That's not an Euler product like defined before. There's an extra factor you have to put in, but it's very easily taken into account. So you can treat that as the definition of the Rankin-Selberg. So this is an L function. We want to bound it on the line a half. Everything happens on the critical line. non-trivially. And the trivial bound for this, or the convexity bound, is k to the power 1. And using families, this method of families, I was recently able to obtain a bound which is better than that, which therefore doesn't completely resolve this problem, but it resolves it for the first time in a highly non-trivial case. I'll state the consequence. I have a separate proof which is independent of these inverted commas, so it's actually a theorem. Yes. What's the point of using bound projectors if you randomly jump? Why am I putting that one here and moving myself back and forth? It's also idiotic. But I must say, I watched some of my Eli Stein do the same lack of agility on moving papers around, you know. Any agility shown will make you chair instantly. If you can staple a few papers, you're chairman of the department. So you have all these guys. Okay, so we do have that bound. The proof uses families, to which I will spend the last few minutes. So the equidistribution conjecture that I stated there is not proved, otherwise I wouldn't have put it up as a problem. I don't view this as a problem like the first two, which are problems for many years to come, perhaps. This, I think, might actually fall in the next few years. It's true for a special kind of modular form, CM forms. So amongst all the modular forms, say the eigenfunctions of Laplacian on the full modular group or some subgroup is a better thing to state, as Henrik was talking about, you have the number of eigenvalues less than t, lambda less than t, because in dimension 2 is about t. About square root of them are these special guys called CM. They are a little more, put your hands on them more easily. And it's quite common in modular form theory to first establish a conjecture for these before understanding the general case. So this has succumbed, even though we know these kind of things are true by the Riemann hypothesis. We actually can sidestep it by proving enough directly. That's a typical kind of thing of when I said you can avoid it and still get the result you're after. So I think I have another 5 minutes. Is that correct? 5 minutes? And let me talk about families for 5 minutes. What is this method of families and why do I push it so hard? Okay. So in the geometric case, the case that Deligne so successfully dealt with, a family is well defined. There's algebraic geometry here, and there's a base space, and there's a family of varieties. So for example, let me give an example. We might have the family of hyperelliptic curves here. Let's take in affine form, of course. In the end, you work projectively, but this is the feature. Y squared is x minus t. T is the parameter. This is a good example. One parameter times a fixed polynomial of degree n. All this is over the field with q elements. And let me assume that the roots of Pn, Pn is a fixed polynomial of degree n, as I said. The roots are distinct, let's assume. Then as long as I keep t away from the roots of Pn, this will be a non-singular hyperelliptic curve. So there's a natural, and t runs in the algebraic closure of Fq. So as t runs in this set of points, I get for each t a curve. And this is an example of a family. And the t is the parameter space. We were talking about parameter spaces are somehow the only things one can really study from many points of view. Now that's a family. Now I'm not going to define this, but there's something called the zeta function associated for a curve or variety of a finite field. I'll call that LCT over FQ. Instead of using the variable s, it's more customary to use the variable t. And instead of writing LS chi, it's usually written L chi s. The object's more important than the variable. So this switch is, because this is customary in a geometric world. And the family here is clear. It's a family of curves, and this is a family of L functions. And what I was saying at the beginning about Deligne's proof that's so remarkable, what's going on here? Is that in order to prove the Riemann hypothesis for this curve, they say it's a new proof in the case of curves, for one of these curves, you put this in a family like this. So we now have a family of L functions with that parameter t. You form a secondary L function, which is associated with the representation of pi 1 of this family, represented on the first cohomology group of a fixed point in the family. And there's a group that comes with this, which measures how these curves move and how these L functions move. That's called the monodromy group. But the key point here is that you have this group, and you have this family, and the group sort of relates for you the different L functions. And by taking a very high dimensional, this was the point that put the zeros closer and closer to the line and a half, by taking very high dimensional representations of the image of pi 1, the monodromy group, high dimensional representations. There he used some work of Kashdan and Margulis about Zariski closure of these Lefschetz pencils, of which you have to compute this here, but using high dimensional representations and a positivity argument, two features I'm going to return to in a second, you conclude the Riemann hypothesis for all the L functions at once, not just one. So you learn it, the first time you learn the Riemann hypothesis is for all of them in the family. The parameter space is important. The monodromy group is important. Now what we're doing over Q in the proofs of theorems like that is similar kind of arguments. So very briefly, suppose I want to prove this subconvexity bound. I have a sum like this. This was this Rankin-Selberg case. I have a sum n. It turns out that this k squared, f, g is fixed, f is weight k, let's say. I have a sum of this product of these coefficients. I have no clue what these coefficients are. They are just coefficients of modular forms. We don't know them explicitly. This is why the subject for non-CM guys, for example, is very difficult. And we want to make a non-trivial estimate there. And already this has been pruned down so that any use of Poisson sum or anything of that nature, approximate functional equation, these are technical things, will only bring you into yourself after application of some duality procedure. So this is the beef. You've got to somehow estimate this non-trivially, now or never. So the idea of families, which is inherent in Deline's method also, is you average these forms you have, you put it in some family, and the choice of family is always very subtle. And in the simplest case, you might take the sum that you want to some power, and there has to be an interplay between how big a family you choose and how large a power there that you can deal with. And of course, in the end, you want to do two things. You want to analyze these averages, and you want to use positivity in the end, it's only two, and throw away, and this is what the Leans use, of course, as well. You throw away all but one term and then say, I get an estimate for one term, even though it's weak, you might say, because I average over the family. But if I increase the power here, I'll learn more and more at each step. So this is how that quantum unique ergodicity theorem that I proved is proven, in fact. You do find the right family and put it in the right situation to obtain a non-trivial bound for that. But then you might say, I didn't know anything about the coefficients. Well, the point is that when you, and this is where modular forms, this is where the techniques of modular forms enter. You want to expand this out and then sum over f. That is then some kind of trace operation, some kind of spectral expansion, and it converts you into exponential sums, like Klosterman sums, perhaps. All these results, which are going to do better than the trivial bound, the subconvexity thing that we are both talking about, all require this, what was the word you used, slogan, off-diagonal analysis. This is where the action always is. So to end, I want to describe a couple of ideas that Katz and I have had in the last 5 years. We've just finished writing a book on this. Perhaps in these families case, you can go much further. Perhaps you can actually see the monodromy group in the global case. What do I mean by that? I have 2 more transparencies. I think it'll be okay. So perhaps there's meaning to the following. Take the original Dirichlet L functions, LS chi, chi quadratic. I claim there's meaning, you'll find this in our works, of that the family LS chi has an infinite dimensional symplectic symmetry. Chi quadratic means these are Dirichlet characters ordered by their conductor, and chi squared equals 1 is the notion of quadratic. On the other hand, if you look at the LSFs, where F are holomorphic forms of weight k, the family I was introducing in that quantum unique ergodicity problem, the symmetry group's quite different. It's an infinite orthogonal group. Now, this is very loose speaking because the notion of a family in algebraic geometry is well defined, but here I'm just taking this set of L functions and saying there's a way that they definitely glue together and perhaps have the features that might be so crucial in such a positivity argument together with, in fact, all the results that are proved, the partial results, are proved this way. But let's try even see if there's a group really underlying this problem. And the way we study this is to look for each L function at the low-lying zeros. So each L function is supposed to have its zeros on the line and a half. I'm just going to motivate this. So don't ask me if I'm assuming Riemann or not and so on. The Riemann's true, so each one has its zeros on the line and a half. And let's look at, as I vary over the family, where the lowest one tends to situate itself. This is something that Katz and I study in great deal in the function field case. And in that case, using remarkably, ideas from mathematical physics, random matrix theory, in particular, a very important idea of Gordon from the 60s. We are able to compute the scaling limit of monodromy groups and determine in the function field, say for the analog of this family, what the distribution of the lowest lying zero is. And it's quite pretty, and it's given by some universal law from random matrix theory, which we identify. In fact, a new distribution that was not known, just by the way. So I've spent with many of my colleagues, like Henrik and some students, and Luo, a lot of effort to try to prove that the same is true in the number field. In other words, that there is such a symmetry group. And this turns out that there are many now results, analytic results, which confirm and distinguish the different symmetries for this family, this family. We have about 9 families we can deal with. And these are theorems that actually prove these results in certain ranges. And more importantly, just like I said, Riemann experimented, we make conjectures with pain. We numerically experiment. And Rubinstein wrote his thesis a year ago with a tremendous scientific achievement of checking these conjectures for various families, and they fit like a glove in the case there. So, not an OJ glove, no. So this leads me to conjecture 4, which I hope is not just born trivially. And this claim is that whatever was true in the function field case, and that's how we determine the symmetry, but then when we do these analytic results, this comes out of the calculations, that's the understanding at this level, that the low-lying zeros, a family of L functions, when you order them by conductor, follow the laws of the symmetry type associated with a family. And I can tell you, for example, that that's the evidence, that that's a symplectic group, that's an orthogonal group. In each case, we can identify. They're scaling limits of classical groups. Okay, I think I've gone over my time, and since there is a discussion, presumably about speculations along these directions, I'll stop there.
Thank you.
If there are any quick questions, maybe not essentially to be answered now, but to be recorded for the discussion, I think this is a good time to ask them. So, Jeff.
Where did it become a low-line zero?
What's the exact definition?
No, I mean, what's the parameter or something?
Yeah, so you have a family like these chi's. They're ordered by their period. So there's, for each q, there's only one chi. Now, it turns out there's no parameters in this theory. So this part of the part of what comes out, you multiply the lowest zero by log q over 2 pi. It sort of wants to come down to the point 1/2. You multiply it by log q over 2 pi, and then it's roughly bounded. And then you vary over q, and you draw a histogram of these numbers. And the predicted answer is Payne-Lavey 5 coming from KP hierarchies for complete.
Where does this infinite dimensional symmetry come from?
I only can tell you in the function field, and when we discuss this, we might of course, the minute you understand that. All I can say is what's very promising here is it shows that what we're looking for, and what I didn't get a chance to address Kahn's work, which maybe we'll talk about it later, or at least say some comments about. But it does show that what you're looking for, I should emphasize that a spectral interpretation of the zeros, which is highly convincing by all these random matrix models, and Kahn has even given a spectral interpretation in the action that he wrote down, which I think we'll definitely return to. A spectral interpretation is one thing. Its power, however, I mean, one knew a spectral interpretation of the zeros in the function field case already in 1931 by Schmidt. This was well understood in terms of Frobenius and Riemann-Roch. It was Weil who realized how to bring in Castanler-Wavers inequality. He gave 2 proofs, other ideas, in order to put the zeros on the line. The fact that you have a spectral interpretation doesn't put them on the line. So you're asking, I think that what's very promising here is once we understand this mechanism, is a very good sign that all these positivity arguments and family things will be there to complete the thing. So what we're looking for definitely is there. But I can't right now, we'll discuss later, tell you what the thing is.
Okay, thank you.